Okay, let us try to find this particular problem. What is the value of ID? So, looking at this particular equation, so it is pretty clear that okay, gate is connected to this VDD, that is 1.8 volt. So naturally, VGS happens to be 1.8 volt. Because we don't know whether the MOSFET is in linear or saturation condition. So let us have the expression for ID in saturation region and try to find out whether the MOSFET is in saturation region or not. The expression for ID sat is half Kp W by L VGS minus VTO or VTH whole square. Because we know all the values, Kp we know, W by L is given here, VGS is 1.8, VTO is 0.4, and upon substituting all these values, so we will get ID sat happens to be 10.88 milliampere. This is the answer. So looking at this answer and this circuit diagram, since 10.88 milliampere, if it tries to flow here, the voltage drop would be 10.88 volts, which is not possible here because your supply voltage is restricted 1.8. So this is not a valid answer for this, meaning the MOSFET is not operating in this saturation region at all. So this is not a correct answer. So we may have to find out the MOSFET when it is in linear region. The expression for ID linear happens to be half into Kp W by L 2 times VGS minus VTO into VDS minus of course VDS square. So this is the expression for ID in linear, but we don't know what is VDS. VD is actually this voltage that is between drain and source of this. So writing the KVL, we can write it as VDD is equal to ID into RD. Of course, let us name this as RD plus VDS. So naturally, VDS will be VDD minus ID into RD. Wherever VDS is there, let us replace it by this particular expression. So you have ID linear is equal to half, okay, let me just write it, half Kp W by L 2 times of course VGS we know as 1.8, VTO also we know 0.4, then VDS now is equal to VDD minus ID into RD minus VDD minus ID into RD whole square. In this only unknown parameter is this ID. Of course, in linear region here also this is ID, this is ID. All other parameters we know. Upon solving this, we will get the expression for two values of ID. Two values of ID in linear region happens to be 1.68 milliampere, and the other value is I'm just writing the values as I got it using the calculator. So since there is a negative value, positive value, negative value cannot be possible. So only this is the possible value. So let us try to find out whether this will be proper or not. Suppose if 1.68 milliampere flows to this, then how much will be VDS? So then VDS happens to be close to 120 millivolt. So 120 millivolt. So which is a feasible answer. So let us go to LT spice and try to simulate the same thing. So this is a value. You can see this is 1K, and then I have the resistance value. Sorry, W by L is given as 10 divided by 0.18. Let us run it here now. So if I can run here, okay, let me just take out this. Okay, let me remove this also. If I run it here and try to see what is the current happens to be, if you can see, it is 1.6869, which is exactly our calculated value also. So our calculated value was let me just make this also half screen so that I can see both of them. Okay, this is 1.68 here. You can see this is the current which we got it as over here. So this is the current 1.68. This is also. We can also see what is the voltage here. The voltage is this VDS. VDS is, we can see this is 130 millivolt. Of course it is 120 because we have actually didn't consider the decimal points, we just stopped at 1.68, but the current happens to be 1.6. Suppose if I just find out exactly what is the current, the current flowing here is 1.68699. if I take all those decimal points, I'll get it close to 113 so and so as the voltage. So this way you can able to find out what is the current through this particular transistor. Now you cannot jump and say it's always in saturation region, because saturation region is ending with 10.88 milliampere. So we need to find out the other possible current, that is when the MOSFET is in a linear region. So it is in linear region with a current of 1.68 milliampere. Let us move on to second problem and then try to see what is that second problem is. So let me just look into that. So we have this as, so this is VDD is equal to 1.8 volt, this is 500 ohm, and this is W by L is equal to 30 divided by 0.18. So again, assuming that this is in saturation, we can write it as ID is equal to half Kp W by L VGS minus VTO whole square. Out of this I know, because I need to find out this ID, so I know this, I know this, I know this, I know this, but I don't know this. I can find the value of VGS. VGS is nothing but voltage, because this is same. Okay, this is VD as well as VG. This is Vs. So if we can find what is Vd, that is VDS is equal to VGS is equal to VDD minus ID into RD. So if I name it as RD. So let me replace VGS by what is this? This is VGS. VDD minus ID RD. So it is half Kp W by L VDD minus ID into RD minus of VTO whole square. Now I know this value, this value, this value, this also known, this also known, this also known. Only these two are unknown values. If we can actually find what is the two possible currents using calculator, so I'm getting the values as ID is equal to 2.09 milliampere and the other one is 3.74 milliampere. 3.74 milliampere cannot be the possibility, because that will end up with more drop here, so you will end up with uh, very less voltage across gate and source. So this is the possible answer for this particular problem. So ID is equal to 2.09 milliampere, which will have a VGS of 0.755 volts, which is also equal to VDS. But VDS sat happens to be, of course, this minus 0.4, which is 0.355 volt. So it is in saturation, so that whatever equation we are just chosen for ID calculation is correct. So let us go to the simulation, try to find out whether the same value comes or not. Okay, let me just take out this. Let me open the second problem. So this is second one. Let me remove this. Okay, this is that. You can see we have the same circuit. WL is 30 divided by 0.18, and if I run it now, the current is supposed to be 2.09 milliampere, which is there. Here you can see it is almost 2.09. The corresponding voltage is you can see the corresponding voltage is of 754 millivolts, which is exactly the calculated also. The calculated was coming out to be 755, which is the same. So this way we can able to now the MOSFET is in saturation. Okay, let us move to next problem. So the next problem we have slightly different. Let me just write the third problem. What we have third problem is, okay, this is third problem. This is 1 kilo ohm. This is 100k given. This is VDD is equal to 1.8 volt. So this is 20 by 0.18 is the WL. Okay, now let us see what is this. Now in the first problem we had a circuit where this was shorted to the gate, sorry, the VDD. Now it is through this resistor. Okay, this is the slight difference here. You can see this is shorted here. This is, there is a 100k coming here. Even though there is a 100k coming here, this IG is equal to 0. There is no drop here, so there is a 0 drop. You can treat the voltage at the gate same as voltage at the VDD point. So in this case also VGS is equal to 1.8 volt. So we can solve the problem by considering this as assuming the transistor in saturation region. So let us, of course, you can start with ID as a linear region also. Let us start with ID in saturation region, and if we find it okay, it is not correct, we'll go to ID in saturation region, so linear region. ID sat happens to be half into Kp W by L VGS minus VTO whole square. So we know everything here. So VGS we know everything. We know upon substituting this, ID sat comes out to be 2.17 milliampere, which is not a feasible answer because you have 1 kilo ohm resistance and then it will not come. Of course, I'm just looking into the answer which I already done it and simply putting the values directly. So let us take ID as linear. We know that when ID is in linear region, the expression for drain current is half into Kp W by L 2 into VGS minus VTO into VDS minus VDS whole square. So since we know VGS is equal to 1.8 and VDS is not always VDS sat, you are right, VDS is equal to, in this particular case, VT minus ID into RD. So you substitute wherever VDS is there by this. So we will end up with ID linear is equal to half Kp W by L 2 times VGS minus VTO minus, sorry, not minus, VDD minus ID into RD minus of VDD minus ID into RD whole square, close the parenthesis. Now only unknown parameter is this ID, because this ID linear, these are the only unknown which are there on either side. We know all other things, so you can see we know all of the parameters, so that you can get the value of ID. Of course, there are two possible values when you do it in calculator. One is 1.74 milliampere, the other value is minus 1.03 milliampere. You cannot have negative current, so this is the possible one. So upon doing this, we will get VDS as close to 60 millivolt. Let us verify the same using what is that, simulator. Okay, it is my simulation. Let me just take out this. Okay, yes. Okay, let me open the third assignment problem. This is that exact equation circuit. This is 100k, 1k. W by L is equal to 20 by 0.18. You run the show, run the simulator. You can see the current happens to be 1. Okay, this is 1.74 milliampere. You can see this is 1.74 milliampere, and the voltage happens to be, the voltage is 57.187 millivolt. We are looking at 60 volt because of this. Okay, decimal points truncation, you are getting it as 60 millivolt theoretically, and of course in simulation it is 57 point few millivolts, 57.18 millivolt. This is how you can able to the takeaway from this is this particular, even though you have a resistance of 100k, there is no gate current, so that's why there is no drop. You have to take VG is equal to 1.8. Since gate is shorted, VGS is equal to, sorry, since gate is source is grounded, VGS happens to be 1.8 volts. So you start from here and then you end up with these two possible values. So this is a valid value. Let us go to the third problem, sorry, the last and the fourth problem, where you had the expression for again finding out the value of ID. In this particular case, the value of the the circuit is slightly different. We have this now. This is RS, this is RD, this is 1 volt, and we have this as 1 kilo ohm. Of course, now we can find out whether the MOSFET is in linear saturation. Again, as I said, okay, W by L happens to be 50 by 2, which is 25, the ratio. Of course, you can take it as micrometer, and this is micrometer, the ratio is 25. Assuming MOSFET is in saturation region, I can write it as half Kp W by L into VGS minus VTO whole square. Now the question is, what is VGS? VGS is not 1 volt. Actually, VG is 1 volt. VS is not grounded. Since source is not grounded, VS is ID into, because same current flows through, whatever current flows here, the same current will come down here. So I will say current flowing through RS is also ID. So I can write VGS as equal to VG minus VS, which is equal to 1 volt minus what is this VS? It is ID into RS. ID into RS. So this way we can able to substitute the values of VGS as so and so. Okay, I will write it as ID sat is equal to half Kp, sorry, W by L into 1 minus ID into RS whatever value minus VTO whole square. Upon substituting, because we know all the values, half we know, Kp we know, W by L we know, 1 volt we know, this is the only unknown, here, this is known, everything is known. Upon substituting, you will get the value of ID. Again, two possible values because we have ID on either side of the expression. It is 583.8 microampere or 15.4 milliamperes. So there are two possible answers. This can't be the answer because you have a 1 kilo ohm resistor. Since you have a supply voltage of 1.8 volt, this much amount of voltage cannot drop here. This is the possible answer. And upon substituting all these things, okay, VDS happens to be, of course VGS happens to be, what is that, 1 minus ID into RS, which is coming out to be 0.882 volt. VDS, which is nothing but VDD minus ID into the sum of the resistance RS plus RD. This comes out to be how much? 1.09 volt. So we shall just verify all the currents and the two voltages. Let us go to LT Spice and then verify. Let me just take out this, say yes. Okay, fourth assignment. Okay, this is that expression. I can see I'm shorting this bulk to source so that we'll get the proper values. Let me run it here. Okay, let me just say it as 1T01 is done. Okay, let me see what is the current. Current should be 583 microampere. It is 583 microampere. You can see the current is 583 microampere. And then we are supposed to see what is VGS. VGS should be 0.882. This is VGS, which you can see, and this is 0.883 point something millivolt. This is perfect. And VDS happens to be, should be 1.09. Let us find out what is VDS between drain and source. This is drain and this is source. This is VDS. You can see it is 1.09. So we could able to verify all the three values, which is over here. So ID is 583 and VDS is 1.09 and VGS is 0.88. So all the values are verified here. See, this is VDS, this is VGS, and this is ID. Where is ID? ID is here. Okay, let me just show you that ID value. This is ID is 583. Okay, this way we can able to very comfortably do the simulation and of course the calculations.